This is tutorial 1 for chapter 5 beams. Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. So the first problems that we are going to solve or try to solve in this video are going to be the sample problem 5.1 taken from the reference book. So in this problem we have a timber beam and a loading as shown here 20 and 40 kilonewtons.
Diagrams and determine the maximum normal stress due to the bending.
So we need to find the shear SFD and the bending moment diagram, and we need to find sigma x. So what we have here is a beam with point A, B, C, D, fixed pin and roller support at D. The cross section is 80 mm of width and height 250 mm. So what would be the strategy to solve these problems? First, what we have to do is to treat the entire beam as a rigid body, okay, where we are not going to assume any pure bending occurring, so the length are going to be the same, and then we are going to determine the reaction forces at point B and point D. So we need to use the equilibrium equation of force X, force Y and moment. And then we are going to section the beam at points near the support from A to B, and then from A to C, and then from A to D. And then we are going to apply equilibrium analysis on resulting free bodies to determine internal shear forces and bending couples. And next we are going to identify the maximum shear and bending moment from plots of the diagrams. And then finally we can apply the elastic flexure formula sigma equal to mc over I to determine the corresponding maximum normal stress at that specific maximum bending moment point. Okay, so let's start answer this problem. So first we are going to draw this free body diagram, okay, where we are going to calculate the reaction force at B and D. So we can easily find the value of B and D by using the force Fx should be equal to 0 and force Fy should be equal to 0 and the total moment should be also equal to 0. So then we can find easily RB and RD, reaction force for both points. So from here we are going to start by calculating the shear and the moment for each section. So we are going to start from the section from point A to the part immediately before point B. Okay, immediately before point B means that we are not going to consider 46 kilonewton. So what we have here is 20 kilonewton at point A, and we have shear force V1 and bending moment M1. So we can use the equilibrium equation Fy equal to 0. Therefore, negative 20 kilonewton minus V1 equal to 0, and we are going to get V1 equal to a negative 20 kilonewton. Okay, then similarly we are going to do the same for the moment. So moment should be equal to 0, and we only have M1 here, and therefore we are going to get 20 kilonewtons times 0. So the distance from exactly at point A is 0 meter. The value of x is 0, and therefore we are going to get M1 equal to 0. We are going to proceed with the next part, okay, where in this part we are going to find V2 and M2, and this time we have a certain distance of x, okay, where the value of x are going to increase from 0 to 2.5 meter. So let's start with the shear force V2. So negative 20 kilonewton minus V2, we are going to get V2 equal to negative 20 newton. So we can say that the shear force from A to B stay constant, and then we have the bending moment 20 kilonewtons 2.5 meter, okay, the distance exactly before point B, plus M2 equal to 0, and we are going to get M2 equal to negative 50 kilonewtons. And we can also represent this as an equation where 20 kilonewtons times x is equal to plus m2 equal to 0. So we are going to get m2 is 20x kilonewton meter. Okay, so if the value of x is 0, so m2 is 0. If value of x is 2.5, then m2 will be negative 50 newton. Sorry, negative. So this is for the value of x from 0 to 2.5 meter. So next, we are going to proceed to the next section from point B to point C. So this time we have V3 and M3, and we also have the reaction force at point B, which is 46 kilonewton. So the calculation would be the same. We are going to use equilibrium force at y-axis, 20 kilonewtons, negative 20 kilonewtons plus 46 minus V3 equal to 0, and we are going to get V3 is 26 kilonewton. And M3 we are going to get negative 50 kilonewtons. Okay, basically we are going to have 20 kilonewtons plus times 2.5 meter plus M3 plus or minus 46 kilonewtons times 0. So we are going to get negative 50 kilonewtons. And next we are going to proceed with the next part from the point of B exactly after B to the point exactly before C. Okay, immediately before C. So this is V4. So we are going to get the same shear force with V3, 26, 26. So the shear force stay constant from point B to point C. Okay, and we are going to see that the bending moment from negative 50 kilonewton increase to positive 28 kilonewton meter. And next we are going to proceed. We are going to get V5 equal to negative 14 kilonewton and M5 equal to 28 kilonewton. So we can also write this as another form. If I can say if the value of x is from, so let's say if we take the value of x is from point A, so for the value of x of 2.5 to 3 meter, 2.5 to 3 meter, the equation that we are going to use will be the equation for this section, where we are going to have the total moment are going to be 20 kilonewton, okay, where x minus 2.5 meter times x, okay, minus 46 kilonewtons times x minus 2.5 plus m3 equal to 0, where we are going to get that m3 is equal to negative 20 kilonewton times x plus 46 x minus 2.5. So exactly at point B, where the distance of x is 2.5 meter, we are going to get the value of m3 is negative 50 kilonewtons. Okay, and if the value, if we increase the section from point B to point C, where we have the value of x, the value of x is from 2.5 to 5.5, okay, 5.5 meter. Then we are going to get the value for M4, which is positive 28 kilonewton. And then if we proceed with the next part, the last part at point D, we are going to get V6 equal to negative 14 and M6 equal to 0. So now we are going to use these values into the diagram. So we are going to convert this value into the diagram. So we have the diagram here starting from point A, point B, C, and D. So what we have to do is just to replace the value. So this point actually just to represent that the value of the shear force is exactly after point A. So basically we can also state that at point A, okay, the value is negative 20 kilonewton for the shear force and stay constant until point B. And then from point B to point C, it becomes 26 kilonewtons when the 46 kilonewton reaction force is included in our shear force calculation. Then we have 26 kilonewton. Then we have negative 14 kilonewtons from point C to D. For the bending moment, so we are going to have a linear slope from A to B, and then from B to C it increases until 28 kilonewton and becomes 0 at point D. So from here we can see that the maximum shear force and maximum bending moment can be identified. So the maximum shear force would be positive 26 kilonewton this point, and the maximum bending moment would be negative 50 kilonewtons, and the absolute value would be 50 kilonewton. So we are going to use this value, and we know that the maximum bending moment occur at point B. So this would be the point where we are going to pay attention a little bit more, and we are going to use the flexural formula to calculate the maximum normal stress at this point B, where it have the maximum bending moment 50 kilonewton. But before that, we can calculate the section modulus using the equation of moment of area of a rectangle. So 1 over 6 BH square. Okay, we replace with the width and the height, and we should get S equal to 833.33 exponential minus 6. Then we use the equation of flexural formula, sigma m equal to maximum bending moment MB over S, and we are going to get the maximum normal stress will be 60 exponential 6 Pascal or 60 megapascal. So this is going to be the maximum stress that's going to occur in this beam AD. So from our calculation, we understand that the maximum stress will be existing here, okay, at 60 megapascal at point B. And what will happen if the yield strength of the beam is lower than 60 megapascal? It means that at point B, okay, the failure are going to start from here. So next, let's take a look at problem 5.2. So we have a structure shown as W250 167 roll steel beam, and we need to draw the shear and the bending moment diagram for the beam and the given loading. Determine normal stress in section just to the right and left point of point D. So we need to find this normal stress before point D and the normal stress just after point D. So the strategy would be to first we need to replace this 45 kilonewton load with an equivalent force at point D. So this force 40 kilonewton are going to also induce force and moment. So we need to represent with an equivalent value, and then we are going to find the reaction force at point B, okay, by considering the beam as a rigid body. So here at point B, we are going to have also a reaction moment, and then we are going to section the beam at points near the support and the load application point. We are going to apply equilibrium analysis to find the internal shear force and the bending couples, and then we are going to apply the elastic flexure formula, sigma equal to mc over I or m over s, and determine the maximum normal stress at the point before D and after D, left and right of point D. So first we are going to replace the 45 kilonewton. So we are going to find out we have a force of 45 kilonewton at point D and also a couple 27 kilonewton, and then we can find the reaction forces. Okay, similarly we can use the equation of total force at y-axis should be equal to 0, and the total moment also should be equal to 0. Okay, where we can represent this distributed load as one concentrated load, 45 kilonewton, can be represented as 45 times the distance is 2.4, so times 1.2, okay, meters. So we are going to get one equivalent force at the distance 1.2 meter from point A, and then we can calculate the force the reaction force at point B, where we are going to obtain 153 and 429.3 kilonewton. So next we are going to section the beam and apply equilibrium analysis on resulting free bodies. So we are going to start from point A to X distance before point C. So what we have here is we are going to represent the distributed load again with one concentrated load. Okay, and we are going to use the equation 45 times the distance x, and 45, this one is not 1.2, 2.4, 2.4 throughout the length of the from A to C. The location of the concentrated load is located at x over 2, okay, half from the distance of x, and we can find the value of shear force V, okay, from this equation easily. 45x minus V equal to 0, and we are going to get V is equal to negative 45x. So the value of V are going to be from 0, the minimum, when x is equal to, so when x is equal to 0, then V are going to be 0, and when x is equal to the maximum distance is 2.4, then V are going to be equal to negative, V will be equal to negative 108 kilonewton. Okay, similarly for the moment, so moment equal to 0, so we have 45x as one concentrated load, time the distance from the section is x, half of the x over 2, plus m equal to 0, and we are going to get m equal to negative 22.5 x squared. And if we continue, next from the point C to the point immediately before point D, so the distance is merely x, okay, but this time for the concentrated load it will be located at a distance from of x minus 1.2, so we know that this is the distance is 1.2 meter. So for the calculation of the force at y-axis, so we are going to have minus 108 kilonewton minus V equal to 0, and V will be equal to 108 kilonewton. And for the moment, okay, we are going to use the force 108 kilonewton, the equivalent load from the distributed load, minus the distance from this point, okay, just immediately before point D, so x minus 1.2 plus m equal to 0, and we are going to get m equal to 129.6 minus 108x. Okay, so the value of x here will be from the distance from C to D. And then we are going to proceed the section from D until B, and we are going to have the load at point D 45 kilonewton and also the moment 27 kilonewton meter. So for this part, okay, the shearing force would be minus 153 kilonewton. Okay, we can do the same process. Okay, so if we want to write the equation, it would be minus 108 minus 45 minus V equal to 0. So we are going to get V is equal to minus 153 kilonewton. And for M, okay, it will be the same. M3 should be equal to 0. So if you want to write the equation, it will be 108 x minus 1.2 plus, so we have this moment, plus M, and then we also have this moment 45 kilonewton, so plus 45 times x minus 3.3, and we also have this moment 27 kilonewton, so it is in clockwise direction, so it will be minus 27 equal to 0. So if we simplify the equation, we are going to get M equal to 305.1 minus 153 x kilonewton meter. So what we have to do next is to insert the value of x, then plot the diagram for SFT and BMD. So we are going to get this diagram for V 108 kilonewton from 0 to 2.4 meter, and then from 2.4 meter to 3.3 meter, the shear force will be constant minus 108, and it will increase, it will decrease more till minus 153 from D to B, okay, for 4.8 meter. For the bending moment, okay, the first equation, if you look at here, it will be a quadratic, and then the second part it will be linear, and then at the third part it will be linear again. So we are going to have the first part is quadratic from 0 to 2.4, and then from 2.4 to 3.3 meter we are going to have a linear equation, and at point D, so you can see that the line is not continuous, and the main reason is basically because at point D we have the moment 27 kilonewton. So this moment are going to be plus, okay, plus from 226.8, okay, plus 27 kilonewton, and we are going to get 199.8, and from there, okay, it will be a linear equation again until point B minus 429.3. Okay, so we are going to apply the elastic flexure formula to determine the maximum normal stress to the left and to the right of point D. So looking at the point D, to the left of point D, the maximum, the stress, maximum normal stress is minus 226, and to the right of point D, it will be negative 199.8. So from appendix C, we know that 250 times 167 steel shape will have a section modulus of 2.08. So what we have to do next is to insert the values that we have for the moment and the section modulus to the flexure formula. So sigma m to the left of D, the maximum normal stress, is this value 226. To the right of D, it will be 199.8, and we should get the value are going to be 109 megapascal and 96 megapascal. So bending moment before point D would be larger than the one after or to the right of point D.